Hello everyone, so today is day 4. We are looking at the problem find if path exists in the graph, and as usual this is today's POTD. So there is a bidirectional graph with n vertices and each vertex is labeled from 0 to n minus 1. So we have vertices from 0 to n minus 1, and it is a 2D matrix which represent edges and edges. So these are not weighted edges, we are just given if the edge exists between two vertices or not, and it is a bidirectional edge. So what we have to do basically with this information is we can make a adjacency list. Every vertex is connected at most one edge and no vertex has an edge to itself. Okay, so there are no self edges, and between any two vertices there is only one edge. So like if these are the vertices, then there is only one edge, there cannot be a edge like this again. Okay, so now you want to determine if there's a valid path exists from the vertex to a destination. Okay, so we don't have to find the path, we just have to check if the path exists or not. Given edges and the integers, return true if okay. So I solved this problem first using DFS. Okay, so before moving to the approaches, let's look at this example. So in this example, this is the graph given. This complete is one graph. It has disconnected components. So let's say this is our source, and if the destination is this, then we can reach here by going here then here. But if we have 1 as our source and our destination is 5, so we have no path from which we can go to 5. So in that case we'll have to return false. Okay, so I solved this problem first using DFS. DFS was really intuitive. Just call the DFS function over the source path, maintain a visited array, and traverse the graph. And as soon as we find the source doing the DFS, we'll return true. So that was the approach that I took, but it was inefficient as it could beat only 50% of the total submissions at most. So the another solution which I came up with was of union and find. Union and find was an efficient solution of this problem, and I will be explaining both the solution in this video. So okay, so first let's discuss the DFS solution. Okay, so let's see the approach one, that is DFS. So if we are given the source 1, so we will call DFS function here, and then DFS function will require an array visited as it usually does, so that we don't traverse the visited neighbors again. So visited, so when we call DFS over 1, we will mark the visited of 1 as true. So it will be an array of the visited array will be of size n, so 0 1 2 3 4 and 5. As you have 6 vertex, so n here is equals to 6. So from source we mark this one as visited, so now it's true, and rest all are false. So now we will check all the neighbors of 1. So for checking all the neighbors of vertex in DFS, we will have to make an adjacency list, which you can see in the code, or we will see in the pseudocode. So the neighbor of 1 is 0, so now DFS will be called on 0, and 0 will be marked as visited. So now 0 is also true, it is also true, and now then we will check the neighbor of 2. The DFS function will be not called on 1 as it is visited here, it is marked true. So then it will check if the visited of true is false, and we have visited of true is equals to false. So DFS function will be called here, and then this 2 will be marked as visited, so this becomes true. Now the 2 has no neighbors, and so it will return false from here. Then this will return false, and thus we have not reached our destination 5, so we must return false here, and that is what returned from here, false. Now let's see another example in which the path is present. So let's take an example. If there was this edge present, let me make it with black color. So let's choose black. Done. So if this edge exists here, so now when we call the DFS function, so again this will become false initially. So false, false, and false. And now we will call the DFS function over 1. 1 will be marked as true. Then DFS will be called on 0. 0 will be marked as true. Neighbor of 2 are 1 and 2, but 1 is already visited, so DFS will be called on 2. So now 2 is also visited. Now 2 has a neighbor here 4 which is not visited, so we'll mark 4 as visited and explore 4's neighbor. So now neighbor of 4 is found to be 5, and 5 is equal to our destination. So we will stop calling the DFS again and we will return true from here. There is no need to call the DFS function over 5. If you find the neighbor to be equal of target, then you can return here true. And now this will return true, this will return true, this will return true, and the DFS function was called initially on 1, so it will return true in the calling function. And thus we found that the path exists, which surely does. The path is from 1 to 0, from 0 to 2, 2 to 4, and 2 to 5. Note that the DFS function can also call DFS of 3 first, and then 3 will go to 5. So as we know, DFS is not always optimal. So this can happen that this will be our path, and we just have to tell that if the path exists or not, so it won't be a problem. Okay, so now let's move to the pseudocode of this problem. Okay, so now let's see the pseudocode of this problem. So the first function will be valid path. Valid path, it is of bool type. It has a parameter, the number of vertices, the edges, the 2D matrix that we are given in the question, the source, and the destination. So first we have to make an adjacency list here. So we are making adjacency list. You can also make an adjacency matrix, but I'm making an adjacency list. So we will make a vector int adj of size n, because there are n vertices. And now we will traverse the edges 2D matrix. So for I in edges, let me show you how the edges look here. So we will, okay, now as you can see, the edges matrix for this particular question looks something like this. So I will go from here to here, and for each I we will get 2 vertices. So let's say the vertices are u and v. So int u is equals to edges of I of 0, and int v is equals to edges of I of 1. Okay, so this is just a pseudocode. I'm not using the for each loop here. So yeah, now adjacency list, we will in the adjacency list of u, that is the vertices which are connected by u, we'll have to push back here v here, because there's an edge, and adj of v dot pushback. As this is a bidirectional graph, the edge will exist in both the adjacency list, not both the adjacency list but the list of both the vertices. So I will move from here, and for this will be a u and this will be a v. So for the adjacency list will look like 0, 1, 2, 3, 4, 5. In the adjacency of list, for this I will push 1, and also for 1 we will push 0. Then for 2, okay, now for this I on 0 we will have to push 2, and also for 2 we will have to push 0. For this I, for as u is equals to 3, we have to push there 5, and for 5 we'll push a 3. For this I, in 5s we will push 4, and in 4 we will push 5, and finally for this I, in 4 we will push 3, and in 3 we'll have to push 4. Okay, so our adjacency list will look something like this. Now as we have made the adjacency list, we will move to the actual calling of the DFS function. So this is over here. Let me right here. Okay, so now we will call the DFS function over the source vertex. So DFS will be of return type, so return DFS adj. I meant DFS will be of bool type, so it will return true or false. We will need a visited array here, as we have discussed. So we will have to make a vector of int visited. Okay, let's make it vector of bool. It takes less space than int, so vector of bool visited, and it will have a size of n, and by default all will be false, so we don't need to initialize it. And we'll also pass here the destination, and yeah, that will be our valid path function. Now let's look at the DFS function. So a DFS function would be of bool type, so bool DFS, and as discussed, it will take the argument adj, the current vertex I on which we are calling the DFS, then the visited array, and then the target. So what we will do first here is, on whatever vertex the DFS function is called, we'll mark the visited of I is equals to true, and now we will explore all of its neighbors. To explore all of its neighbor, we have made the adjacency list. So what we'll do is, for int j on the adjacency list of I, so what we are basically doing here is, if DFS function is called for 0, it will the j will traverse on the list corresponding to 0. So j will traverse on this. So first j will be 1, then j will be 2. Let's copy it down, so if we need it we can use it. So yeah, now for int j across adj of I, what we will do, check if the j, the neighbor, is equal to our target. This means we have reached the destination. So what we have to do here is return true, as the path exists. If it is not equal to target, then we will have to explore further. So but we will only explore those nodes which are not visited. So if is not visited of j, we will call the DFS function for j. So we'll call the DFS function DFS ADJ. Now the current vertex is j. It will need the visited and the target node. Now we'll call the DFS function, and DFS function will return either true or false. So we have to check what is the DFS of for j. So if DFS of j, that is if this returns true here, what we will do is we will return true from here. We will not explore the further neighbors of I. If we get true, we will return true from here, and therefore this will go for all the neighbors, and if none of the neighbors were able to return true, this means that the path does not exist. So at last we will return here false. Okay, so that was our DFS function. So what's basically happening here is the j will go to 1, and then DFS function will be called on j, and now j will be marked as visited. This will be marked as visited, and DFS function will be again called to 0, but 0 is already visited, so DFS function, this condition will not reach, and DFS function will not be called on this one. It will return from here as no name. It will return from here false, and then the 1 returns here for false. Then j will move here, and then for that will be called for 2. And also, as we can see, are we making no. Okay, so the mistake is that the DFS function will not be called on 0. As our source vertex is 1, so DFS function will be called on 1. So as DFS function is called on 1 in this example, so we will move to 1 neighbors, and then from 1 this is visited, so DFS function won't be called here. Then DFS will be called on 2, and as 2 has no neighbors and 2 is not equal to target, it will return false from here, and from 2 it is returning false, and from 1 it is also returning false, so this will return false to 1. If this any vertex has a path, so for example our source is 3 and our destination is 5, so DFS function will be called on 3. Okay, and then okay, it is already reachable, so let's not take this example. I think we should take, okay, so if our source is 0 and our destination is 2, okay, let's say source is 1 and destination is 2, then what will happen is DFS function will be called on 1, then 0's neighbor will be explored, and then 1 will be explored. 1 is already explored, so DFS function won't be called over it. Then 2 will be explored, and as we see that the adjacent, as 2 is equal to our destination or the target, so it will return true from here. So it will return true, and this will return false. So we are only checking if the DFS is true. So for false, it will move to the next iteration in the loop, but as for 2 it comes to be true, the function will return true to 1 here, and as it is true, the answer will be returned, final answer will be returned true. Okay, if you have any further doubts, then you can see the code. The link is in the description. Okay, so now let's move to the optimal approach of this problem. A better approach to this problem would be union and find. In union and find, we don't even require the rank vector. We can do this only by union and find and the parent vector. So if you don't get it, don't worry. Let's move to the dry run. So our source is 1 and our destination is 5. So what we will do, that we have the adjacency, we don't even need to make the adjacency list here. We will have the edges matrix and we will traverse the matrix. And so what we'll do is, as we are given an edge 0 to 1, so we can say that 0 is connected to 1. So let's say 0 is connected to 1. Then we are given 0 is connected to 2. Okay, so we can say 0 is connected to 2 and 0 is connected to 1. So we can say that there's a path from 1 0 to 0 to 1 and there's a path from 0 to 2, and the edges are bidirectional, so automatically there will be a path from 1 to 2 as well. Okay, so let's see the next eye. So it's given that we have edge from 3 to 5 and then we have edge from 5 to 4. If we have an edge from 3 to 5 and 5 to 4, we can reach 3 from 4 and 4 to 3. So we can say this. So what we are basically doing here is, from each edge we are making the union set, that okay, these are reachable from each other. So next we have 4 to 3. So yeah, 4 to 3 already exists path. As you can see that you can reach 4 to 3 from here as well, and you can reach 4 to 3 from here as well. Okay, so yeah, and now we can say that 1 is in different set and 3 is in different set. So there's no path from 1 to 3, there's no path from 1 to 5, there's no path from 1 to 4. So what we do is that if the source and destination are in the same set, then these are reachable, they have path between them, and so we'll return true. And if they're in the different sets, then we must return false. So how can we do this is by using an array parent. Parent will be having the size that of the vertices. So here there are 0 1 2 3 4 and 5. Okay, so initially let's say there, every from source to itself you can reach there. For example, if I say the source is 1 and the destination is 1, although there is no self edge, but you are at the destination, so you can reach there. So we can say that from 0 you can reach 2, from 1 you can reach 1, from 2 you can reach 2, from 3 you can reach 3, from 4 you can 4, and from 5 you can reach 5. So initially the every vertex will have parent as itself. Okay, now we will have two functions here, find function and union function. What this find function will do is return us the parent of any node. As we saw that we were making a set something like 1 to 0, 1 to 2. So what we are basically saying is that parent of 0 is 1, parent of 2 is 1, and parent of 1 is 1 itself. So we are doing this to find if they are in the same set, and in the another set we have 3, 5 and 4. So parent of 5 is 3, parent of 4 is 3, and parent of 3 is 3. So if the source and destination have same parent, so we can say that they are in the same set or they have a path existing between them, so we will return true. Then for union, what we will call this union on every eye, for every edge. So while doing so, we will update the parent. As we are making the tree like structure, actually we will be updating this parent array by finding the parent of both of them and making an edge. For example, if we see the set, we had trees like 1 0 and 2, and here 3 4 and 5. We don't require the rank vector here because because we don't need to like worry about on which we are making which vertex the parent. We can make any vertex the parent. So now if we are given this edge, this 2 to 3 edge, so now let's say our edges will come 2 to 3, and now the parent of 2 is 1. So in the union function we will find the parent of 2, which will be 1, and for parent of 3, which is 3 itself, so we can say that the edges between them, so we need to update the parent. So the parent of 1 and 3, what we will do is either make 1 the parent of 3, or you can also make 3 the parent of 1. So what this basically does is that now, as we can see, all the nodes are reachable from each other, and we can also say that if we are doing this, the 3 is parent of all nodes. So on whatever function, on whatever node we will call the find function, it will return us 3. So basically it means we have path from every vertex as the parent is same. Okay, so now let's move to the pseudocode of this problem. Okay, so let's first see the find function. So our find function will have 2 arguments, the array parent and the vertex I for which we want to find the parent. So it will be a recursive function if we can say the parent of I is equal to I itself. So we will return the parent itself. So we will return the I itself. So we will return I. Else, if the parent of I, this condition is false, then we will make a recursive call here by returning the find of parent array will be as it is, parent, and the parent of I. What this basically means here is that, let's take this part as an example, this part as example. So what this find function will do is, let's say we call find function on 2. So parent of 2 would be 0 and parent of 0 is 1. Okay, so parent of 0 is 1. What we want is the top node as the parent. So all the nodes which are connected to it will be considered having path between them, and that is they will be considered at one set. So if we had more vertices, for example 7 or 8, all will have had parent 1. So now the thing is that it will be really inefficient every time we will call this find function over 2, or as the depth increases we'll call this find function over multiple vertices, and every time it will make recursive calls up to 1 to get this one. Another way around this is what we call as path compression. So what path compression does is that as we find that the parent of 2, as we call the find function, will return 1, why don't we update at the parent of 2 as 1 only? Why do we need to traverse the whole tree again? So path compression, making path compression here is really easy. You just need to add this here. We will add return parent of I is equals to find, and whatever find will it return will be saved to parent of I. So next time when we need to find the parent of I, it will be like parent of 2 is equals to 1. So that will be really easy for us and less time consuming. Okay, so now let's see the union set function. So we will have here union set. I'm using the word union set, not union, because union is a keyword reserved in C++. I don't know for what it is used, but it is there. So for union set, we'll have two vertices, u and v, the parent vector, and you can have also the rank vector if you want to merge any two vertices based on rank. We are not discussing it here now because it is not required in this problem. So let's say if we have a parent, now what we'll do is find the parent of u and v. So we'll find the parent u and parent v, and okay, no, there won't be any brackets. So parent v and parent u, and parent, as we can see, we have written the find function. We can find the parent by find, and what we will do here is find the parent of v, will send a parent and v. As in the find function, we have parent first, then the vertex. So find parent v, and for u we will say find parent and u. So now that we have find the parent of both of them, we will see if the parent is same. So what we will do is we will see if parent of v is equal to parent of u. So if both of them has same parent, so this means that they already belong to the same set. So we don't need to do anything. So we will return from here. Else, if the parent of them are not same, then we need to add them to the set. Add them to the set, what we will do is we can make the parent of u and parent of v to either make the parent of u as parent of v or make the parent of v as parent of u. So what we will do here is we will say parent in the parent array of parent of v is equals to parent of u. By using the rank vector, what you do is instead of just arbitrarily choosing a vertex, you will have another array to calculate the rank of both the parents, and according to the rank, whose rank is higher, we will push that vertex into v. So what this does is as the lower height tree is inserted into a higher height tree, it doesn't increases depth much. But if a higher height tree is inserted at the lower height tree, then that will increase depth like a lot. So let's not go there. We'll just have the union set function here, and now what we have to do is only write the driver function, or we can say the valid path function. So valid path function here has n the edges, source and destination. So we will have one vector here, vector int parent. It will be of size n, and we will have to initialize this parent by itself. As we have discussed initially, each vertex is parent of itself. So what we will do is for int I is equals to 0, I less than n, I plus plus, we will do parent of I is equals to I. So this is done. So now let's move on to traversing the matrix itself, traversing the edges matrix itself. So for I in edges, what we'll do is the first vertex will be int u is equals to edges of I, j, I and 0, and that will be edges of I and 1, that is int v. And now we just have to call the union set function over them. Union set u v parent. So now that union set will make all the sets, and that will be represented in the parent array. So now what we have to do after making the sets is just to check if the parent of them are same. So we can do this by calling the find function. So we can say if find parent of source equal to find parent destination. If this is true, then we must return here true as the path exists, else we will return false. So that will be our valid path function. So that's nothing but that's valid path function. Yeah, so that's all for this video. I hope you like the solution. If you have a better approach or better solution to this problem, all the links are available in the description. Okay, so thank you for watching. Bye bye. Now